在
Calculus. Okay guys, we're back into it. Section 4.6, linear approximation and differentials. So, the idea here is one of the key ideas for the whole class. This is one of the most fundamental parts of calculus. This is really everything that's going on under the hood. And this section is surprisingly banal given how important this idea is. So, imagine plotting a smooth curve with a graphing utility. In fact, we don't have to imagine it. We'll do it in just a second. So if we pick a point P on the curve and draw a line tangent to the curve at the point P, zoom in on it real close, what you notice is that if the function is nice, it basically looks like this tangent line near that point. So this is the fundamental idea of calculus. This is kind of the entire motivation. We can understand curvy lines, more complicated stuff, just by noticing that when you zoom in real close, they look like straight lines. That's really all that's going on here. That's pretty much the entire idea of this whole class. So this idea, which we can, conveniently or maybe pretentiously describe as local linearity, the idea that if you zoom in very close and you look at a curvy line, it looks like a straight line if that curvy line is sufficiently nice. This is the basis of a lot of important mathematical techniques. One of the most useful ones is linear approximation. That is, just using the equation of the tangent line at a point, you can approximate the value of the function quite well near that point. In fact, you can approximate it to arbitrary precision if you're close enough. Okay, we'll talk a little bit more about what that means, but let's just look at the basic definition. The linear approximation to a function f at a point a. So if we suppose that f is a differentiable function on an interval I containing the point a, then the best linear approximation to f at the point a is the line, the linear function L of x equals f of a plus f prime of a times x minus a. This is the best linear approximation to that function near that point. Now I know there's a lot of quantifiers there, so let's look at the picture and make sure we really understand what's going on. Okay guys, we're back. I got a tangent line flying around on a cubic right here. Got some sort of a cubic, got a tangent line on it. It's just playing it out. And let's just pause it at literally any place. Let's pick a kind of nice looking one. How about right there? Bam. Okay. Now we can see that these guys, they're passing through at, this point right here. Yeah? Let's zoom in really close. Okay, the line doesn't look too straight quite yet. But let's get closer and closer and closer. And oh my gosh, that is getting pretty gosh dang close to a line. Yeah, if I zoom in all the way, I mean, not all the way, you can never go quite all the way, but if I go real far, you can't even tell the difference. I have to zoom out a fair bit to even start to see those lines split off. So, this is the gist of it. This is the tangent line to this graph here, and if I zoom in extremely close on any given point, and look at how the tangent line compares to the graph of this function, it's pretty easy to see that nearby I'm getting almost the exact same things. Let's see, can I get this to grab them both? No, I can't. Okay, well, you can see very, very close between the two of them. And if I zoom in close enough, I can get so close that you can't even see it. Pixel for pixel, those are the same line right here. Now, in reality, there's always something lost when graphing. In reality, no graph of a function, these lines don't have any thickness in reality. But in terms of whatever level of precision you want, you specify how close you want it. You can find an interval around a given point for which the linear approximation given by the tangent line is within that margin of error. So, cool. And notice, there's something cool going on here. There's something that we'll talk about in a little bit here, very understandable happening. Namely, notice this line is below this graph over here. And if I start to let it play again, let's see, there we go. Notice that the line's above on this little chunk over here, and it's below on this chunk of the graph over here. It seems like it switches from being above to below at 0, 0 right there. This might remind you of a concept we've talked about recently, maybe concavity or something like that. So we'll talk about this more in just a little bit, but notice when the tangent line is below the graph, the linear approximation is underestimating the actual value of the function. And when it's above the graph, it's overestimating the value of the function. So we can actually use this to our advantage quite easily. It's kind of nice. But let's get familiar and do a super intuitive and very useful example. Okay guys, here we are with an example. This is a good one because you can actually use it. So, let's suppose that you're driving down a road. And if you've ever driven down a road, you've probably noticed there are those little green mile marker signs every so often. Mile marker, right? Those are some really terrible squares. But you get the gist of it. There are these mile markers not every so often, in fact, about every mile, I would say. You got these little mile markers here and there, and as you're driving down the road in your little car, having a great day, you're just sitting in your car and you're driving, you're just going down the road, and you notice the mile markers pass as you're driving. So, as these mile markers pass, you can generally estimate your speed. For example, say you see a mile marker and you glance at the clock in your car and you see that it's like 3:52. You see another mile marker a little bit later and you see it's 3:53. I would say that you're driving about 1 mile every minute or about 60 miles per hour. So let's suppose that if you that you're doing this and you just measure how many seconds more or less than 60 seconds it takes you to go from 1 mile marker to the next. So, x, let's let that be the number of seconds more or less than 1 minute it takes you to go between mile markers. Okay, we can actually make a pretty cool little formula right here. So, since there's 3,600 seconds in 1 hour, that is, there's 60 times 60 seconds in 1 hour, let's make a function, let's call it s of x. And if we take 3,600 divided by, let me write this slightly nicer, 60 plus x, then notice, here's what we got. If this is number of seconds in 1 hour, and this is the number of seconds it takes you to drive 1 mile, then s of x is giving you your speed in miles per hour. Exactly that. Oh, takes a bit to write this down. All right, but basically the gist of it is, imagine, you're on a long road trip, you're trying to figure out about how fast you're going. Hopefully your speedometer works, but maybe, you're just trying to get a general sense of it by seeing how fast those mile marker signs pass. You could count it off, and see, okay, saw one, saw another one. Okay, maybe I did it in, it was 63 seconds between those 2 mile markers. Then x would be 3, and this would give me that I was, or how about let's take x to be 2. I've already computed that one. So if it took me, 62 seconds to go between them, then I would get out the value of about 58.06 if I plugged in 2 for x, and that would tell me that I'm going about 58 miles an hour. So if it takes me around 62 seconds to go between mile markers, I'm going about 58 miles an hour, as opposed to 60 miles per hour when it takes me exactly 60 seconds. So if I, if I'm going 1 mile in, say, 57 seconds, if I get there quicker than 1 minute, then if I plug in s of -3, since I'm going quicker than 60, or I'm getting there faster than the 60 seconds, I'm getting there in 57 seconds, then I get out about 63. So that's telling me that if I go from mile marker to mile marker in about 57 seconds, then I'm traveling at about 63 miles per hour. S of x gives you exactly your speed in miles per hour based on this, the average speed over that last mile. Okay, cool. So we don't want to use a calculator while we're driving. I think that that's fair enough. I think that computing 3,600 divided by 60 plus x is not something that most of us are going to be pretty good at doing in our heads. So let's derive a linear approximation to this function. Okay, here's the gist of it. We're going to take s of x and we're going to find its first derivative, s prime of x. So I could write s of x, if you're all right with this, as 3,600 times 60 plus x to the -1. Doing this, it becomes pretty straightforward to see that I can just use a little bit of chain rule here and get that s prime of x is 3,600 times -1 times 60 plus x to the -2. And this is just a little bit of chain rule. I'm just bringing that -1 down. I'm subtracting 1 in the exponent. And then when I multiply by the derivative of the inside function here, that's 60 plus x, that's just 1. I'm not even going to bother to write it down. All right, cool. So I get 3,600, or more accurately, negative 3,600, over 60 plus x, that whole quantity squared. All right, so let's compute this at 0. let's find the linear approximation, L of x, to S of x at x equals 0. Remember, this is important, the linear approximation is given at a point. It's not a linear approximation to the function everywhere. As we saw in that last little example with the graph, we were picking the tangent line through a point on the graph, and it was only a good approximation near that point. So let's find the good approximation near x equals 0. How about it? Why not? Let's try it out. Okay, so first thing we'll do, it'll be L of 0 plus L prime, I'm writing L's when I should be writing S's. Sorry about that. S of 0 plus S prime of 0 times x minus 0. Just the good old-fashioned equation of a tangent line. I can figure all this out pretty easily. So S of 0, 3,600 times 60 to the minus 1. That's just 3,600 over 60. 3,600 is 60 squared, so you get 60 right there. All right, S prime of 0. So if I go on through and I plug it in, what I will find is that I'll get minus 3,600 over 60 squared. Since 3,600 is just 60 squared, I could write this slightly more conveniently as just 60 minus x. Hey, that's not so bad. That works out okay. So if you didn't catch that, I'm going to write the full step down right there. I'm going to write out the missing piece, and then we'll talk about what this 60 minus x means. The basic gist of what's going on here is that we've just figured out how to approximate our speed without barely even having to do anything at all. So let me write this bad boy down real quick. Okay, there's the missing steps that I just talked through. And there we go. At the end of the day, that's 60 minus x. This tells us that if it took us x seconds more or less than 60 to travel 1 mile, if that's how long it took us to go from 1 mile marker sign to the next one, we know our average speed over the interval pretty close just by subtracting the number of seconds more, or, if the seconds are negative, less, from 60. So if I travel 1 mile in, say, 57 seconds, then my average speed is about, something in the neighborhood of, let's see, L of, 57, that'll be L of minus 3, right? Because 57, that's 60 minus 3, yeah? So 60 minus negative 3 is about 63. Okay, so if it takes me 57 seconds to travel 1 mile, then my average speed is about 63 miles an hour. This is a great trick. This is a kind of cool little trick. If you're sitting in the back seat of a car and you can't see the speedometer, you can kind of wow someone by telling them about almost exactly how fast they're going. They'll be like, whoa, how did you know that? Or they probably won't be surprised because, you just might know the speed limit. But, hey, in practice at least, kind of neat that you can do this in your head. Way cool. Let's go on. Okay, guys, we're back. So if you've ever seen that movie with Matt Damon where he's a janitor, the one where he's good at math, then you know that you can impress people by doing things in your head. I don't know why, but that's a thing. If you can do virtually any math thing, even just kind of adding fractions, the average person will act like you're some sort of strange god. Weirdly true in my experience. But Here's a great way to do it. This will wow people super hardcore. A great trick to do at parties if you don't like getting invited to parties. So let's figure out how to compute sine in our head, provided that sine is pretty close to 0. So let's find the linear approximation to the function sine of x at x equals 0, and let's use it to approximate sine of pi over 72. So we'll construct a linear approximation using the formula for the equation of a tangent line. So L of x will be given by f of a plus f prime of a times the quantity x minus a, where here f of x is sine of x and a is 0. So since sine of 0 is just 0, and since f prime of x is cosine of x and cosine of 0 is 1, we get that L of x is just 0 plus 1 times x minus 0. It's just x. So our linear approximation yields the estimate that sine of pi over 72 is about pi over 72. Something in the vicinity of 0.04363. And if you punch it in an actual calculator, you'll find that sine of pi over 72 is about 0.04362. So this is accurate out to about 4 decimal places. That's pretty cool. Now, maybe it's not as much fun to do sine. If someone's like, oh my gosh, man, what's sine of pi over 137? And you're like, about pi over 137? It doesn't seem as impressive. However, if you do it with, say, like cosine, that's a little bit more fun. So if we did cosine, which, because this is going to be super easy, we can just do it right over here. So if we did cosine instead, near 0, notice that in that case, we would get, well, it's going to be cosine of 0. Now, the derivative of cosine is minus sine, so minus sine of 0 times x minus 0. Okay, now if we run through and do this, cosine of 0, isn't that just 1? Yeah. Sine of 0 is 0. Hey, a good approximation to cosine near 0 is 1. Cool. So if someone's like, oh, what is cosine of, oh gosh, pi over 139? You could be like, oh, God, I think it's just a little bit less than 1. And people will be like, oh my God, he's right. And, then, I don't know, you'll win an award and you'll be popular at school. So, cool. Computing sine. Let's do some more. Okay, guys, so just like when we were talking about concavity when we first started looking at that graph, concavity plays a role in whether or not a linear approximation at a given point is an overestimate or an underestimate. So, when f is concave up on an interval containing a point A, then, now I'm just going to sketch a quick tangent line right here. Some function and a tangent line. Notice this guy is concave up and the line is below the graph. That means that it's an underestimate. All of the y values coming out are strictly smaller. So I could pick a point and notice that, if this is over some point here, that the values coming out on the y-axis, if I throw in some axes over here, are lower for the points on the yellow line than they are on the blue curve. So when the function is concave up on an interval containing a point that you can differentiate your function at and find a tangent line, then that tangent line is going to underestimate the function near that point. Now, it's not the case that it's an underestimate everywhere, but near the point, it's an underestimate. Just to see that, take something like a cubic, something like a terrible looking cubic like that. Then if I pick some point, say, I don't know, let's pick one here, something like this. Then I could be an overestimate for some parts and an underestimate for other parts. That is, this guy is below the line over here, and it's above the line over here, or the curve. So it's only nearby a point that we can use concavity to tell whether or not it's an overestimate or an underestimate. And this isn't really a deficiency in any way. The real thing to keep track of here is just that these are only good estimates near the point in the first place, so who the heck cares if they stop being good estimates far away from a point? You know, they're not even good estimates way far away, and so who cares if they stop being underestimates and start being overestimates or vice versa? All we're caring about is nearby. So here I've got a concave down function, and you can see very easily that the line is above the graph. And once again, for the same reasons, we will end up getting an overestimate this time. So you can use the second derivative to tell whether or not a linear approximation is an overestimate or an underestimate. Cool. In fact, we can actually go even further than what we just talked about. So pretty much as far as we've gone so far, or everything we've talked about so far, we're just using concavity's sign. We're saying, is it concave up or concave down? Is the sign of the second derivative the only real important thing? No. You can actually get information about how concave a function is just by looking at the second derivative's value. So this is generally called curvature. And this tells us something about the degree of concavity. Basically, the way you can think of it is that the absolute value of the second derivative at a point is the curvature of the function, if you want to think of it like that, the curvature of the graph. This says if you've got a large value of f double prime of a, an absolute value at least, big and positive or big and negative, then near the point a, f of a, the slope of the curve changes rapidly, and the graph separates extremely quickly from the tangent line. A small value of f double prime of a, either big and positive either small and positive or small and negative, so in absolute value, just a small number. This means that the slope of the curve is changing slowly, and that the curve is relatively flat near a, f of a. So this is saying the slope of the curve changes slowly, curve is relatively flat. Before, we have that the slope of the curve is changing rapidly, and the graph separates relatively quickly from the tangent line. So absolute errors in linear approximations are larger when f double prime is large in absolute value, i.e. when it's big and positive or big and negative. What does this mean? We can just kind of draw it out, and it starts to be a lot clearer. So basically the way you can think of it is that if you pick something, sufficiently nice, maybe just a line, this guy doesn't have any concavity at all. This has concavity 0. It's not concave up or concave down anywhere, right? Okay, fair enough. Let me just kind of draw a box in here and see if I can get a good picture sort of going for us. So this is the situation where we've got concavity 0. Now, as I vary things a little bit, I could, instead have it go, let me see if I can draw this a little bit better, like this. Now I'm concave up, albeit only very, very slightly. If I keep going, I can see that I could make this like an extremely concave up sort of thing, right? And do something like this. So down here, these are places where we have positive concavity. We can go exactly in the opposite direction. We can get just very, very, very slightly concave down, We could go way more concave down, do something a little bit wild. I'm kind of running out of colors here. Do something like whoosh, like this. Okay, this is telling us these places over here, this is when we have negative concavity. Basically, think of it like this. Think of it like you've got some sort of a slider. I'll just sort of draw in a little slider here. Oh. From this corner of the box to that corner of the box. And you can just take your little dial and you can dial it into any one of these things, right? It's like you could just slide along the thing, and as you move your slider from here on over to here, you're deforming this line from this guy into that guy. And when you hit the middle of the slider, you get that zero concavity, and as you go to the other side, you get positive concavity. So you're going from negative to positive as you slide across this thing, and you're just bending the lines. Think of it like this is a rubber band. That yellow line is a rubber band stretched tight between, two nails or something like that. And this slider is just you pulling it from one end to the other. This is what concavity is measuring. This is basically what the second derivative is telling you, how bent this line is. And the bigger and positive concavity is, the further down in this corner it is, right? More like this shape. And on the other hand, if I'm over here, if I have a big and negative value for my second derivative, then I've really bent it in this direction over here. So concavity, kind of cool. Tells you something about curvature, how deformed your line is in either direction. Neat. And this lets us know whether or not our linear approximations are overestimates or underestimates. Now it kind of makes sense why we even bother to talk about concavity. Fun. Let's do an example. Okay guys, we're back with the last example of the day, example 18. Let's find the linear approximation to the function f of x is the cube root of x at the points x equals 1 and x equals 27. Then let's approximate the cube root of 2 and the cube root of 26. We're going to find out whether or not these approximations are overestimates or underestimates. Then we're going to figure out what the error is on these approximations. We're going to figure out which error is greater, and we're going to even figure out why. So let's just jump into it. Let's figure out exactly what's going on. So the first thing we're going to do is we're just going to start in order. We're going to find the linear approximation to the function f of x is the cube root of x at x equals 1, and then we'll find it at x equals 27. So let's notice that f of 1 is 1. Let me grab a different color here. So f of 1 is 1 because 1 times 1 times 1 is 1. So the cube root of 1 is 1. And f of 27 is 3 since 27 is just 3 to the third. Cool. Okay, so let's just remember really quick that we can write f of x. We can write the cube root of x as x to the 1/3. So f prime of x is just going to be 1/3 x to the 1/3 minus 1. That is to the minus 2/3. So the first derivative, f prime of x, is 1/3 x to the minus 2/3. All right, fair enough. Ooh, and I think I've got a parenthesis wrong on that bad boy. Sorry about that. I did not need a parenthesis right there. Cool. All right. Fair enough. Sorry about that. But now we can just go right on. So f prime of 1 is going to be 1/3 since 1 to the negative 2/3 is still just 1. And f prime of 27 will be 1 over 27. So if you want to see this, f prime of 27 is just 3 to the third. So I'll write it as 3 to the third. What I'll get out is I'll get 1 over 3 times 3 to the third to the minus 2/3. Now, what's going on here? This third and this 1/3, this minus 2/3 here, what I'll get is I'll get 1/3 times 3 to the minus, what? Is it going to be to the minus 2? Yes. So what I'll see here is that I have now, well, this will be 3 to the minus 2, that's minus 9. 1 over 3, I could rewrite that as 3 to the minus 1. This is really 1 over 3 to the third. And as we know, 3 to the third is just 27. So f prime of 27 is 1/27th, and f prime of 1 is 1/3. So let's keep track of our two linear approximations here. The approximation at 1, let's denote that as L1, and the approximation at 27, let's denote that by L2. These guys are just given by L1 of x is 1 plus 1/3 times x minus 1, just using the good old-fashioned formula we've been doing the whole way through. We're getting that 1/3 from that f prime of 1 right here, and we're picking up that 1 from the fact that f of 1 is equal to 1. Fair enough. And with L2, it's the same stuff. L2 of x is 3 plus 1/27th times x minus 27. So we can use these guys. We can just plug stuff in. We're asked to approximate the cube root of 2 and the cube root of 26. So when we approximate the cube root of 2, we're just going to throw 2 right on into L1. And we'll say, hey, the cube root of 2, it's about L1 of 2. And that's around 4/3. So notice what's happening here is I just have 1 plus 1/3 times 2 minus 1. So that's 1 plus 1/3, that's 4/3. And that's around 1.33. Similarly, when we find out what the cube root of 26 approximately is, we just plug it on into L2. We get L2 of 26. Plugging it in, we'll get 3 plus 1/27th times 26 minus 27. So that's 3 minus 1/27. So what we'll end up getting here is around 26 over 27 plus 2, something in this vicinity. So this is around 2.963. Doesn't matter so much how we got there. You can always just punch this in a calculator. Don't pretend the arithmetic's important. We've got machines for it. So now we've computed estimates of both these guys. We've said, hey, the cube root of 2 around 1.333 and the cube root of 26 around 2.963. So let's figure out whether or not these are overestimates or underestimates without even bothering to compute the error. We'll compute the error in a moment. We've got it right down here, but we don't need it quite yet. So let's just show that we can do it without even ever bothering to find out what it actually is. We can know whether we have a little bit more or a little bit less than the actual value. So all we got to do is we just got to take our first derivative right here, and we got to take another derivative. So just a little bit more power rule. We're going to skip over that for now because, you've got plenty of practice with power rule by now, right? So f double prime of x will just be minus 2/9 times x to the minus 5 over 3. Okay, fair enough. So just checking some stuff out with this function, just looking at what's going on. It's only got one 0. This bad boy only has a 0 when x is equal, well, it doesn't actually have a 0 at x is 0. It's got no zeros, but it's got one critical point. There we go. So this guy has one critical point. Since this exponent's negative, I can't plug in any zeros or anything like that. I've got one critical point, and so there's only one place where this guy can change sign. That is, if you look, you can't plug in 0, so try something like 1, try something like -1, and you'll find out that f double prime of x is less than 0 when x is greater than 0. And this tells you that f is concave down for both x equals 1 and x equals 27. That is, the graph of f of x is concave down on the interval from 0 to infinity. So both those guys fall into that area. This tells us, since concave down means that our tangent lines lie above the graph, that both L1 and L2 lie above the graph of f, and that both approximations are overestimates. Now, if we actually go through and use a calculator, we can find out the error, see how far we really are away from the actual value, and we'll see that L prime of 2 minus the actual cube root of 2, we're pretty close. We're about 0.073 away from it. And if we do the same thing with finding the cube root of 26, our estimate there, and we see that the absolute value of L2 of 26 minus the cube root of 26 is about 0.00047. So it looks like my estimate of the cube root of 26 is way better than my estimate of the cube root of 2. They're both pretty good, but man, that's a lot of zeros right there compared to that 1 right there. Okay, so why is this happening? Well, we can figure it out by looking at curvature. So if I find out what f double prime of 1 is, what the second derivative of f is at 1, and just look at it in absolute values because all I care about is the magnitude, what I'll see is that f double prime of 1 in absolute value is about 0.22, while f double prime of 27 in absolute value is about 0.00091. Wow. Okay. This explains why this guy is such a better estimate than this guy over here. Okay, this explains why the error is so much smaller for the cube root of 26 than it is for the cube root of 2. It's because the curvature of f is way greater at x equals 1 than it is at x equals 27. Cool. We learned a lot of stuff. Good.